In this session, we are going to discuss about a new topic which is called Doppler effect. And I think this is a very familiar topic for us because we learned this effect in our lower classes. Since this effect, this phenomena was discovered by a scientist called Christian Doppler, so it is called as a Doppler effect. You can see picture of that scientist in your screen. So he has given this effect, that's why it is called Doppler effect. And when we talk about the Doppler effect, the simple example we always give is a observer is standing in the railway station and the train is blowing horn and coming towards observer, and when the train is coming towards observer, he will hear a loud in a sound, and when that train moved away from his, gradually the sound heard by him decreases. That means the frequency heard by him gradually increase as the train approaches him, and the frequency that he has heard will be gradually decrease as the train goes away from him. So this is what we always give as an example. Then what actually Doppler effect tells? See, before Doppler effect, we have explained, we saw different theories of light, among which Huygens proposed light travels in the form of wave. And using that wave concept, Doppler was able to do a phenomena, and it was called as a Doppler effect. So what Doppler stated is, when a source which emitting the radiations means light, if it is emitting the light or if it is emitting the sound waves, and if that object is moving towards the observer, then the frequency that he measured will be very high, and when the object, the train, when it moved away from that observer, then the measured frequency will be a lower one. So this is what he observed. That's why this is called as a Doppler effect. And he explained this phenomena using the wave concepts. So we already know about wavefront. So wavefront means it is a location of points which are in the same phase. That means all the disturbances are in the same phase, then their locations together can be called as wavefront. So in this picture, you can see an ambulance which is blowing the horn, and you can see some circles, and these are actually called as wave fronts. So this is blowing horn, and the waves from this ambulance are going in all directions. So we can draw spherical wavefront. So these are the spherical wavefront, and they are moving. And if you look at the wavefront in the forward direction, there is a less gap between the wavefronts. If you observe the wavefront in the back of a ambulance, then there is a large gap between the wavefronts. So this indicates that high frequency of wave in the forward direction and low frequency in the backward direction. So that's why Doppler effect plays a very important role, because in Huygens theory, we can, using the Huygens theory, it is able to determine the new position of wavefront in a later time t. If you know a wave at some time t, then you can draw or you can see the position of that wave in some other time t. But that Huygens theory was a limitation that or in other words what we can say is, and Huygens theory was proved when object and observer were stationary. Doppler did a different phenomena, that what if the object and sources are moving? What will be the what happens to the frequency when there is a relative motion between object and the source? If this, for example, if the source is moving towards observer of a observer who is stationary, if both the source and observer are moving, if they are moving in the same direction, if they are moving in opposite directions, then what happens to the frequency heard by frequency measured by that observer? So this is all about Doppler effect. So that is why I told it is a very it played a very important role. So let us see the definition for Doppler effect. I said it already. What is this? It is what happens is, it is apparent change in the frequency which is measured by the observer when there is a relative motion between the observer and source. If the source and observer are moving, if they are in a motion, then there will be a change in the frequency of this. If it is a sound wave, then there will be a change in the frequency of sound which is heard by the observer. If it is a frequency of light, then there will also be change in the frequency which is measured by the observer. So this apparent change in the frequency because of the relative motion between the observer and source, and this whole effect can be called as a Doppler effect. And this Doppler effect is used in the astronomy. Actually, this result was taken by Hubble, and he used same concept into the astronomy. Then what is help of this model in astronomy? Which is nothing but this is helpful in measuring the velocities of the distant galaxies. So the actual velocity is a radial velocity. So radial velocity means it is a velocity of the body along the line that joins the object to the observer. So this is called as a radial velocity. So that's why this theory is helpful in finding the radial velocity of a distant galaxies. Now let us see. Let us see the explanation for this model, this Doppler effect. So to explain this Doppler effect, we need to consider one source. See, there is a source which is moving in a direction of the front observer. Also there is a back observer. See, as the source is moving towards in a direction or moving in a one direction, the gap between the wavefronts decreases, and as the source is moving from another observer, the gap between the wavefronts increases. So this is what we can observe here. So if the source is continuously emitting the wavefronts, then what will happen is, then the measured time interval between any two successive wavefronts which reaching the observer is longer than it was produced. What happens is, See the source producing the waves continuously. If you take two wavefronts, if you take two wavefronts, and we can also measure the time interval between those two wavefronts produced by the source. Also, we can calculate the time taken by those two wavefronts to reach the observer. So, when the observer measured the time interval between those two wavefronts, which will be longer than it was produced. So, as a whole, what I can say is the time interval between the two wavefronts at the source is smaller or shorter than the time interval which is between the two wavefronts as measured by the observer. So what was the observation is the time interval was longer by the two wavefronts when they were reaching to that observer. Hence, what we can conclude is, hence observed frequency is lower when object is moving away from the observer. So, what happened is, if the object is moving away from the observer, then observed frequency is lower. You can see on the screen. Since the object is moving away from the observer, the frequency is lower. So if the frequency is lower, then wavelength will be longer. Then how to say frequency is lower? I told you, when the object is moving away from the observer, the time interval between the two successive wavefronts which reaching the observer is longer than it produced. As the time increases, time interval increases, frequency decreases, because time and frequencies are inversely proportional. So T is equal to 1 by mu. Mu means frequency. So they are inversely proportional. That's why as the time interval increases, frequency will be lower. So when this happens when object is moving away from the observer. If the object is moving towards the observer, then what will happen is the time interval between the two successive wavefronts which reaching the observer will be shorter than it was produced. So at the production of the two wavefront will take more time than the time interval between that two wavefront reaching the observer. That's why time is there is a which takes a less time. So as t decreases, frequency will increase. That's why when object move towards the observer, observed frequency will be higher, because time is a shorter one. So if the time t is less, there is a high frequency. So this is what observed by Doppler. That's why this effect is called as a Doppler effect. And this was observed for sound waves. So Doppler was done this experiment. He done this for sound waves. But the same result was applied, the same concept was applied to the astronomy by the scientist called Edwin Hubble. So in the previous case we told that there will be decrease in the frequency, as well as there is a increase in the frequency. So astronomers call this increase in wavelength. See, there is a if the frequency is if the frequency is lower, then there is a shorter wavelength. If the frequency is higher, if the frequencies, you can see here, if the frequencies are lower, then wavelength is longer. If the frequencies are higher, then wavelength is a shorter one. So this is what we know from the previous concepts. So this astronomer call this increase in wavelength as a redshift. Okay, if there is an increase in wavelength is increasing, then there is a lower frequency. So they said that this is, since this is happening, since the wavelength of the visible spectrum is shifted towards the red end. What astronomer observed is the wavelength of the visible spectrum. We know about the visible spectrum. The visible spectrum contains 7 colors, and which is a waveguide, and this is a frequency that human can identify, which is in the electromagnetic wave. So if there is an increase in wavelength, then the astronomer called it as a redshift, because the shift in the wavelength of the visible spectrum towards the red end. You can see on the screen there is a object is rotating, and it is emitting the radiations, which is in the form of wave. As it approaches towards the earth, so it means that object is approaching towards the earth. So as it approaches, you can see the variation of that wavelength of the visible spectrum towards the two ends. See, now it is blue end, moving towards the blue end. Now it is moving towards the red end. As object is approaching the earth, the wavelength is shifting towards the blue end, and as object is moving away from the earth, wavelength of that light is approaching towards the red end. See, red end. That's why this is called red shift. So since increase in wavelength is called as a red shift, since the wavelength of the visible spectrum is shifted towards the red end. See, shifting towards the red end. Similarly, if source is moving towards the observer, then the observed frequency will be higher. Hence, wavelength of the visible spectrum shifted towards the blue end. So it is called as a blue shift. So you can see this object is moving away, so it is a red shift, and it is moving towards this, so this is called as blue shift. So this is what Edwin Hubble applied Doppler effect. That's why in the beginning I told you the Doppler effect is helpful in determining the radial velocities of distant galaxies. That means if any galaxy is moving towards us, then we can observe a blue shift, so that frequency will be very high. If that galaxy is moving away from us, then we can observe red shift. That means the frequency will be very low. So using this concept, the scientists were able to say that the universe is expanding, because they observed the red shift. So when they look the visible spectrum of the waves which are emitting from the different galaxies, different planets, they observed red shift. That's why they told the whole universe is expanding. See, this is the use of this Doppler effect. So this is about the Doppler effect.